time contact. But at least in the first part of this mission, almost all those bits of ones and zeros coming back to us have been images. The videos that you saw, these spectacular panoramas, lots of engineering data and telemetry, but the imaging data is the vast majority of that stream of radio signal.
All right, let's turn to the freezing cold nights of Mars. Taryn on Facebook asks, will Perseverance send in a night landscape shot?
Well,
the
thing about yeah, absolutely. What I really encourage people to do is imagine that you're the camera on Mars, because our mast is up, and actually the mast is at about 6 feet. So as we look around, it's almost like you're standing there yourself looking around. And they are visible cameras. They're primarily length that you can see with your eyes. And so if you're there at night on Mars, how much could you see? Well, it's really dark, so we can't see a whole lot. And that's where we're at. We're not going to take images at night for that reason. And also because it's the cameras, it's the mast, massive mast that you saw, that has to be heated as well. So you want to set it up beforehand. So all you have to do is open the shutter to take the image and then be done with your job.
I'll just add that, you're absolutely, that's a great description and all that kind of stuff. So for imaging, it's difficult. Photography kind of data out of that. So we can see bright stars. We can see Phobos and Deimos, the moons of Mars. And we'll do some of that science. We'll do some of that nighttime science. It helps us understand the atmosphere and the moons themselves. And it's sort of great bonus science. If we have the power to run the heaters, if we have the power to run if there's scientific questions and scientific interest that we can direct at it, we'll do that. And we'll also, I predict, nothing is formally planned, but I predict we will do some relatively fun kind of things, like take some pictures of the Earth. This has been done on previous rover and lander missions. We will take one, these are the ultimate selfies, right? Everybody on the Earth in that one pale blue dot in the sky. And so we'll probably do some sort of.
There's actually some pretty amazing images from Viking with frost on the ground. So it happens, but it will be frost condensating because the atmosphere is so thin that the water can be a gas or it can be ice, a frost, but it cannot be liquid. And so it will go to frost on the ground and then it will go straight back up in the atmosphere. But you can get, especially if you're not on the equator or close to the equator like we are, you can get a frosty morning that like you can get here on Earth.
And Rachel on Facebook asks, how do you deal with dust on the lenses?
Oh, that's a great question. I get that question every single time. That's a wonderful question. We actually we don't do a lot about it. Actually, we mitigate. We prevent dust from collecting on the lens by pointing the cameras down when we're not using them. That end of the mast, we just point it down, and that prevents the dust that's always falling gently out of the atmosphere from collecting on our lenses. But we know that dust is going to collect on our lenses when we're imaging, and especially up in the sky and all that. We can't point down all the time, and we don't have any little wiper blades or anything like that. No covers to protect them. So we know that the lenses still see through them. Right, and it's not that bad. You get a little bit of dust, and so we can live with that. And if it does get a little thicker, we can correct for that with our calibration that Kjartan and others are working on. And secondly, what we've discovered in previous missions is that once in a while, the winds of Mars come and they blow the dust off the deck of the rover, off the calibration targets, off the lenses. And so Mars has been actually pretty helpful in past missions in keeping our lenses clean. But our prevention is really kind of passive and just point them down.
I'll add a little something to that, because exactly this reason of the dust is why we had to get going really quickly with our imaging. We wanted to take images as soon as we could of a clean rover deck. Well, as Kjartan can attest to, it wasn't entirely clean because, all the dust that was kicked up. But specifically for Kjartan and the other scientists on our team, Jim being another big proponent of this, we wanted to look at the deck as cleanly as we could so we can compare that to all the data that comes after. And that was one of the big reasons we were allowed to image as early as we did. And in fact, even the day before we imaged this one, we took a huge amount of calibration target data. And that was really so that the calibration could compare to that for the rest of the mission. And we'll continue to do that and monitor, take images on a regular basis to monitor the dust that's accumulating. And it's my understanding, Kjartan, that there's some special places on the CalTarget that deals with dust.
Maybe we could show
if you can
image
put
8
up
again.
slide 8, image 8. So it's obviously a problem for the calibration target too, that is always facing upwards and dust will drizzle on them. No, slide 8, the major slide 8. So they will gradually get dusty, and sometimes the dust will get blown off a little bit and they will get dust. That's the one. And actually right at landing, there's a bunch of dust that gets kicked up by the rockets, right? We wanted to image it right after landing as quickly as possible. That's the cleanest it's ever going to be. But it has these, you can see how the dust just rings around the patches. And that's because we build in these very strong hollow cylinder magnets that are sitting right underneath those surfaces. And they attract the dust to where the magnet is, but in the middle, the magnet is not. And that area is kept fairly clean. So we're going to keep those little areas pretty much clean of dust. And those colors are going to be like they were in the lab when we measured them. And we're going to be trusting them still. But another thing is that on other parts of the calibration target, it will gradually get dusty and we will be able to monitor that. And that's actually kind of a little extra piece of meteorological data, because we can sort of tell when the dust is falling and when it gets blown off, and it's like a seasonal thing on Mars.
I'll mention that Kjartan wrote a great blog piece on our public website, and Marina will give you the address at the end, all about this target and all about the magnets and why the colors were chosen and the little messages and vignettes and all that, and the sort of artistic elements that we were able to put on this with help from the Planetary Society and Mark Hilverda, who's an artist who works with the Society, and a small group of us on the team. So I encourage folks to check out Kjartan's article that's on our website.
And speaking of that, for Kjartan, J.E. Bruce on Twitter wants to know where he can get his hands on one of those sundials. And can you tell us more about the sundial?
Maybe I should start a company and just crank him out and sell them.
Right.
We have a few spares. When you send an instrument, you have to build a flight spare in case something goes wrong with the instrument before you launch. So we actually have 2 flight spares. They're not for sale. And we have a few extra sort of test units, but it's only a little handful, and they'll probably wind up in museums where you might be able to see them. Tim has a 3D printed version there, and we do have 3D print files that maybe we'll put out at some point.
Maybe we should put the 3D print files on our public website if you're willing to do that.
Yeah, we could do that. Yeah, sure, absolutely.
So this just gives you a sense of scale. This is full size.
Yep.
So there it is. And we did have, you mentioned museums. We had the flight spare for the Spirit and Opportunity CalTarget was on display in the Smithsonian for many months.
It was cool.
Special exhibits about those rovers. So lots of people put their eyes on that one.
Yeah, I remember I went there, Jim, and I wrote that I just came back from standing in the August presence of the Apollo 11 command module, and you wrote back, how about the August presence of the Spear PanCam CalTarget?
Yes.
And I said that was a flight spare. It wasn't a flight CalTarget.
Yeah.
Anyway.
Well, as a meteorologist, we're getting tons of weather questions. So I'm really excited about that. Everyone is very excited talking about the weather on Mars on social media this afternoon. Chopra on Facebook asks, any storms expected there, and how do you manage them, and how would they affect the Mastcam-Z?
Yeah, I mean, we don't manage the weather. We do not manage it. Absolutely. But you know, the great thing about the fact that we've had 60 years of exploring Mars with flybys, orbiters, landers, and rovers is that we really know a lot about the weather, and it is very repeatable from year to year. Not precisely. Some years are different. Some years have these big dust storms that cover the whole planet, and we don't really understand why those form in some years, not others. But in general, you know, everywhere on Mars has a dusty season and a less dusty season, and there's always small dust storms all the time, and sometimes it's cloudy and with water ice clouds, and sometimes it's not. But we understand a lot about those patterns from these previous missions. And so, you know, we landed at a time that's not particularly problematic for dust storms, but there will come a time when there will be more of an issue for dust. It's not so much of a concern for Perseverance and Curiosity, nuclear-powered rovers, as opposed to the solar-powered rovers, Spirit, Opportunity, and solar-powered missions like InSight. You know, ultimately it was Mars dust and dust storms that killed both Spirit and Opportunity because of the dust settling on those solar panels and the dust darkening the sky and cutting off their solar power. So we care about the way it changes temperatures. We care about the way it could mess up our lenses. So we do follow it and track it and pay attention to it. But honestly, we mostly care about it scientifically because it's a really interesting part of the weather. And we're trying to learn as much as we can about the weather on Mars so that once future astronauts and settlers go there within the next few decades, they'll have a really good understanding of what to expect and when at different times of year. Elsa.
Yeah. And then there's also a little story about how we captured some sand in the cameras with Curiosity. Right. That gave us a nice lesson learned for this mission. So what happened was during dust storms on Mars, sand would deposit. We have these long lens covers that keep stray light from coming into our images. Well, they're also really good at trapping small amounts of sand. And we didn't even think about this until one day when we were looking up at the sky, as we talked about, and we take images, you know, at different angles to look at the atmosphere. And we noticed there seems to be something off. There's definitely something off in these measurements. And we looked into it further and we compared, you know, over time, how did this exhibit itself? And Mark Lemon, who's one of our most prominent atmospheric scientists, looked at his data as well. And we realized there's something in front. There is absolutely something in front. So we took some experiments and we determined that, yes, indeed, when you go up and when you go down, it looks different. Just very proof, really, strong indicators, we say in the scientific world, that we had sand inside the lenses. Well, you can't just go up there and sort of shake it out, right? That's not how it works. So we still have a little of it inside the covers on Curiosity. And what we learned from that was on these cameras, we drilled a little tiny hole in the enclosure so that if we do get sand inside this time, it will trickle out on its own and we won't have this problem again.
Yep, little drain holes. Good lesson from Curiosity. Yeah, it's actually kind of amazing that little sand grains are hopping across the surface and bouncing up 6 feet and going into the front of our, the lenses are set back a little bit. There's like a sunshade and a baffle, so there's a little bit of volume there. And on Curiosity, they're hopping up in there, getting in there. It's totally surprising.
Or getting,
it's like the storms are not, the storms, you know, the winds can be high speed, but the atmosphere is so thin that the power in them is not very high. It's not like it's going to jiggle the rover or tip it over or anything like that, but it can still move sand and obviously dust, but it's kind of surprising how much it can move sand, even though it's such a thin atmosphere.
Yeah, it's like that carved rock, you know, how long it took to do that. You know, that a lot of people have seen the movie The Martian, and there's that scene in the beginning with this violent storm. You know, I mean, it's a dramatic and fun scene, but it's science fiction. I mean, it's nothing like that. I mean, the wind speeds can be very high, but it would be like somebody blowing up, you know, feathers by you. It would feel just so light. It's so thin, but it moves sand and dust very efficiently.
And you're constantly looking towards the future. And so DBL on Twitch asked, what changes have you made to the rover design to better suit the conditions of Mars, which I think Elsa just answered with adding those holes so that you are able to get that dust off. So we'll move on to Harry on Twitter, who's asking, could you please describe the software you're using to stitch together that panorama? Is it custom software developed in-house or using commercial software like Lightroom or Photoshop? If custom, what operating system is used?
Go ahead, Elsa.
Great question. Yeah. Do you want to start, Jim, or you want me to take it?
You start and I'll finish.
Okay, sounds great. So could we have that picture again with the frames on it? It was a second, I think it was number 5. Yes, perfect.
Yeah.
That is such a great depiction of what my life, what our team's life looks like on a daily basis. This is homegrown software. As I mentioned before, John Proton wrote it. He was actually way back on MER, going back now almost 20 years. He was one of the operators that would do commanding and then realized at one point, you know what? I can do this software much better than anything that's commercially available, anything that people have thought of, because he did the job. And then he took his software programming skills, put the two together, and came up with this tool. And it truly is the only software of its kind on this planet. So it's specifically customized for visualizing, imaging, and this is just one way of looking at it, but there's a lot of details that goes into it that's at our fingertips. The distances to each part of the image, what the focus would be that would correspond to it. There's just a tremendous amount of power behind it. So we're extremely grateful to have this. And in fact, it's thanks to Jim working on PanCam with John. And then we did a beta version for Mastcam on MSL that we've been running now for years. All of it with the thought that we would get this tool for this mission with these cameras. And it is spectacularly paid off. It is exactly, I mean, it's more than I could even imagine. You know, Chris and I were talking the other day, one of my ops engineers, and he was just laughing. He's like, I cannot believe this piece of software. I don't even know everything to do with it yet. I can't wait till we can explore it more. And we all feel like that. It's amazing.
So there's a lot of custom homegrown software, but we also do occasionally use Photoshop or those kinds of commercial tools to finish some of the processing and stitching. So it's a mix.
And like you, oh, sorry, go ahead. Go ahead.
Yeah, I just wanted to finish up on the question, the operating systems. We really use all kinds. We're using some of my team runs on Macs. We also have some Dells. We use Linux. And just throughout, we are a team of hundreds of scientists and engineers. If you count them all up, there's probably thousands. And we use all kinds of tools, make them all work together. Our tools that we run for the mission that all of us run have to run on all those well-known platforms.
Yep, and there's all kinds of programming in C, Python, MATLAB, IDL. I got some old Fortran stuff that I can still use. You know, it's a real wide array of programming.
Not only a wide array of programming, but it's a village. And thank you so much for everyone's questions out there on social media. So many of you joined us today, and we'll try to answer some of your questions as we progress through the rest of the day and tomorrow. But thank you most of all to Jim, Elsa, and Kjartan for joining me this afternoon.
It's been a lot of fun, and we just have to thank all of our teammates on the Mastcam Z team, on the entire rover team, the NASA JPL team, the folks who built the rocket, the folks who got through COVID to get us to the launch pad. I mean, what an incredible team! Thousands of people involved in ultimately getting to this kind of spectacular imaging.
Yeah, thanks for having us.
Thanks so much,
really
you guys.
Exciting.
Yes, thanks for having us.
Oh, thank you so much. We can't wait to see the rest of the panoramas. Now, for the latest on the mission, follow @NASA Persevere on both Twitter and Facebook. And you can also take a deeper dive at the mission's website, mars.nasa.gov mastcam.com/perseverance. And as Jim mentioned, there's lots of information about the Mastcam Z instrument on the website mastcamz.asu.edu. And the very latest images can be found at mars.nasa.gov/Mars 2020/multimedia/raw-images. A lot of great feasts for the eyes, as Jim likes to put it. Now, thanks so much for watching this afternoon, and go Perseverance.
A blinking star is only a vague promise. And when have we sought comfort in the mystery of hope? So tell us, there is a way to transcend the elms and basswoods. Tell me about the lives at risk to capture their wondrous bellies. That they too are desperate for more than faded dots beyond reach.
We copy that, and preliminary owns 241 plus 05.
Copy, Columbia.
Scientists hover around computer consoles and await the first image that will prove that Chandra is a revolutionary telescope.
Tell me that the first light is the sprinkling image of a star exploded from bearing our daily requests.
They will not be disappointed.
Astronomers worry about two very large questions. How does the universe work, and where did it come from? In this program, we consider both these questions on the nature and the origin of the universe.
We like to understand the things around us, to explain them. We don't like uncertainty, a mystery. And the sky at night, you just have to look up there and you go, what are all those dots of light?
Humankind, we've always been discoverers, so we want to understand everything that surrounds us. Missions like Chandra provide an additional window into those questions.
It's very much this process of constant discovery and constantly moving those questions forward until you're asking things that you never expected to even be able to ask.
I have an 8-year-old, and she actually asks me about once a week, have we seen all the way back to the Big Bang yet? Why not? When are we going to do that? Mama, have you seen all the way back yet?
It was during a 1962 rocket flight led by an incredibly profound individual named Riccardo Giacconi. This rocket unknowingly detected these 9,000-year-old photons from this distant, incredibly bright, incredibly mysterious system that we didn't even know existed. And in that very moment, even though they didn't know it, they gave birth to the field of X-ray astronomy.
The primary scientific objective that was written down in the proposal for Chandra was to resolve the X-ray background.
They knew the science that they wanted to do. The technology to do it didn't actually exist. Countless engineers had to solve a whole host of problems to get Chandra on orbit. The mirrors on Chandra, those mirrors had to be smooth to the level of a couple of atoms. You're skipping photons, so they need to be atomically smooth. And they have to be really delicately aligned because you need all 8 mirrors to be working together, right? And they are now focusing on an instrument, and the instrument chips are only 4 inches square. And you have to hit that 4-inch square every single time. And that's not actually good enough. That would just give you a blob. So to get the imaging you want, the resolution you want, you have to hit exactly the same spot on that 4-inch square every time. And the spot you have to hit is less than the diameter of a human hair, 10 meters away. Then you have to do this on Earth, but it's going to operate in 0G. So you need to figure out, how can I align these so that they'll be aligned on Earth for testing, but then when it's up in space, it has to stay aligned. You can't go up and fix it. So how do I build all the structure around it so that they stay aligned so precisely through all of that? So once you've done that, you have to make sure that you're controlling the temperature of those mirrors to within fractions of a degree. But you're in space. It's a harsh environment. The engineering and the level of testing and trying and retrying and testing to get just the mirrors right is absolutely mind-blowing.
And those mirrors, they are absolutely the most pristine X-ray mirrors ever flown, and they give Chandra its incredible power.
Less than 1 minute away now from the 95th space shuttle launch. 35 seconds. T-minus 30 seconds.
When Chandra went up on the shuttle, so the shuttle basically lit up the sky like daylight for a couple of minutes as it went up, and the ground underneath our feet shook.
5, 4, 3. We have a go for engine start. 0. We have booster ignition and liftoff of Columbia, reaching new heights for women in X-ray astronomy.
We were 2 or 3 miles away. So it's just an amazing feeling of the power that is needed to escape the Earth's gravitational pull, which we needed to do to get in orbit. And also amazing to think that mankind can actually do this. It's very satisfying and exciting to see the results of all the years and all the people who've worked on Chandra, and finally it goes up.
It was the largest payload the space shuttle had ever launched. There were inherent risks in that launch to the crew specifically. And when we talked to Eileen Collins, who was the woman that commanded the NASA space mission, she talks about them and just very calmly tells us how much they trained for any of those contingency plans, that they had total faith in the operators and the mission control engineers and the flight crew, that they felt they knew this stuff in and out and they could get it done. And they did, literally risk their lives to improve our X-ray view of the universe.
I can't imagine what it was like in the control room watching the first light of Chandra and opened its aperture door and actually collect light from the universe for the very first time. when the first X-ray photons actually landed on the detector. Those photons that landed on the detector were the culmination of decades of dreams and the aspirations of many, many hundreds of really brilliant scientists and engineers, and frankly, their families. I can't imagine the emotional relief there must have been when that exquisite image of Cassiopeia A started collecting. You could quite literally see Cass A become populated with these photons. And this absolutely beautiful demonstration of Chandra's spatial resolution, the image that ultimately came down was a completely transformational view of Cassiopeia A.
It was a revolution.
The elements in that star are the same elements on Earth, the same elements in our body, right? It's our oxygen rich and it's iron rich, and these things that are out in the universe, you know, when you see a supernova remnant, that is what life is made of.
This is really the only way that we can peer into the inside of a star, is really by looking at how it explodes and what the stuff that used to make it up does to the surrounding materials. At the same time that there's these beautiful images that every time you look at them, you continue to fuel your own curiosity towards it.
We are on this tiny little planet next to a very ordinary star that's in the middle of its life, in a fairly normal spiral galaxy in some corner of the universe. And the universe is huge, and there are billions and billions of stars and billions of galaxies and supermassive black holes. And yet we are sitting on this Earth, and we're able to understand at least some of what we're seeing by just looking.
So there was like totally new science learned in the very first observation of Chandra. I can't imagine what that was like. And when it actually came in, I'm sure there were huge sighs of relief and tears of joy and excitement for the future.
There are moments, I think, where I just feel like the absolute luckiest person in the world because I get to look at this data, look at this information, look at these views of our universe. And it's kind of like having the best seat in this ancient cathedral.
The cosmos is all that is, or ever was, or ever will be. Our contemplations of the cosmos stir us. There's a tingling in the spine, a catch in the voice. A faint sensation, as if a distant memory of falling from a great height. We know we are approaching the grandest of mysteries. The size and age of the cosmos are beyond ordinary human understanding. We wish to pursue the truth, no matter where it leads. To find the truth, we need imagination and skepticism. The cosmos is full beyond measure of elegant truths, of exquisite interrelationships, of the awesome machinery of nature. The surface of the Earth is the shore of the cosmic ocean. On this shore, we have learned most of what we know. And the water seems inviting. Some part of our being knows this is where we came from. We long to return, and we can, because the cosmos is also within us. We're made of star stuff. We are a way for the cosmos to know itself. The journey for each of us begins here.
These images portray so much more than what you see on the surface, right? You know, there's information about energy levels and structure and chemical elements in each one of those images that you see, which are so beautiful.
Chandra allows us to directly observe the most extreme events in our universe.
There are jets streaming out from black holes stretching for thousands of light years into space. There are black holes that can sing a note so deep that no humans can ever hope to hear it.
We didn't know that stars could emit X-rays, for example, on the way they do it. We didn't understand how stars blew up. We didn't understand black holes in nowhere close to as much detail as we do now. We don't understand the clusters of galaxies that make up the web of space-time in the detail that we understand it now. Chandra represents a huge step forward in astronomy in general.
We ask things about what's out there. They help us understand ourselves. When we learn about something there, it tells us about something here. And Chandra has been an incredible workhorse to provide some of that information.
From the furnaces of cosmic change, to the birth and death of stars, to, the shining poles of Jupiter, to black holes at the edge of time, and everything in between. You compare what we knew about our universe in 1950 to what we know today, there are multiple cascades of paradigm-changing revolutions that have happened in those intervening decades.
It's hard to convey sometimes that Chandra really is one of the most important astronomical missions in the history of astronomy. It totally changed the way we look at many different phenomena.
I think succeeding in a mission like that is just an amazing feeling. So you then look for the next thing and say, well, we did that, so let's see if we can do more. There are many, many more questions that we need to answer.
There's this common goal at the end, is to getting this mission and answering these really big questions about the universe, right? What we're doing it's really cool stuff. If you stop and think about it, it almost restores the wonder that you had when you were young. You look at these images and they're beautiful and they're captivating, but then you look at what they're conveying and you start to understand the science and you find your sense of wonder again and you start